Okay, so just again, remember that enzymes accelerate the rate of the reaction uh, relative to uncatalyzed. And the way that this works, again, is that the enzyme catalyzed is going to lower the activation energy, the EA. And also remember that there's a number of intermediates in the reaction. And so if you were to look at the reaction coordinate diagram, there would be different energy peaks and valleys as it went along, because there is different states happening between the enzyme, substrate, and product, and they're distinct states. There's not just the transition state. Remember, there's the enzyme substrate complex, the enzyme product complex, etc. And so again, one thing that we didn't talk about before is too much is the K-cat, and this is the turnover number. So this is the number of molecules converted to product per unit time. This is the same, you might have heard it talked about in other types of catalysis, or even maybe a catalytic converter with a car. It's all the same. So turnover number is the rate of conversion from substrate to product per time. And just reminding you, mechanistically, just going back. So the two physical steps here, sorry, there's a colon and there's nothing there. The things that I wanted to tell you, there are two physical steps in enzyme catalysis are substrate binding and product release. So the substrate gets converted to the product while it's bound to the enzyme. And so we consider there are two physical interactions, basically the substrate binding and then the converted product being released. And just as a notice, sometimes that K-cat, this turnover number, is faster than either of these, in which case the catalytic rate is a function of the physical binding of the substrate and release of product rather than the chemical conversion. Does that make sense? So K-cat normally would be telling you how fast this chemical reaction is happening in the enzyme, because it's telling you how many substrate molecules are turned over into product per unit time. But some enzymes are so fast that the binding of the substrate and the release of the product is actually the slow step. For example, superoxide dismutase, the enzyme that gets rid of reactive oxygen species in your body, so peroxides and stuff like that that are super toxic and very destructive. That's an example of an enzyme where the K-cat is so fast that it's really it's only limited by how the rate is only limited by how fast a peroxide molecule can bind to the enzyme, and so we call enzymes like that diffusion limited. It's pretty neat stuff. Okay. Now we're going to talk more about mechanisms, and as medicinal chemists, we use this mechanism a lot, an understanding of the mechanism to help us inhibit enzymes. So this understanding the enzyme mechanism is incredibly critical to controlling enzyme activity. You have to understand how they work. And so there's a number of common mechanisms. General acid-base catalysis is very common, electrostatic catalysis, etc. One of these I think is interesting is that the enzymes accelerate the rate by what's known as approximation. In this case, they mean rate acceleration by proximity. So reactive groups are held closely enough in the enzyme that the reaction happens more quickly. And you can think about it, it's almost like this is a thermodynamic principle, Le Chatelier's principle, but it's almost like having a really high concentration because of something, because everything, the reactants are so close together that it's like they're extremely concentrated. And so you can think if you had a crappy reaction but had the two reactants right next to each other, you would probably increase the likelihood that they would bump into each other in just the right way, that you would get a product, or you get the transition state, right? That they would react. So this is a takes you back to statistical mechanics. I don't know if you guys have had that yet. But the other, so basically it's equivalent to increasing the concentration. So another example is covalent catalysis, where something's covalently attached to the enzyme. So this is very common. So you have typically what'll happen, well, almost always what'll happen is that the enzyme will covalently attach itself to a substrate, and then the product will leave. And so this is common. A common method of catalysis, and it's something that we deal with and can inhibit. Now there's two kinds of acid-base catalysis, right? We have specific and general, and we talked about this and last time, but one of the things that I wanted to show you last time that I didn't was that general acid-base catalysis, the graphs that would be associated with this.